Okay, here we are again. I've recovered from my cold, and I feel like that we can zip through this without too much trouble. I want to ask those of you, I've sent you an email, and everybody in here that's working in this class should be reading their email and responding to it. It's one of your responsibilities. So make sure that you do so. Alrighty. Yes, okay, give me a moment here. Can I get moving any moment? And let's see here. Okay, let's see. Okay, yes, you keep hearing me say okay, but we're getting with it here. Hold on a second here. Okay. Alrighty. Okay. Thank you for waiting there. I was working with my the technology. Okay, let's move on. Thank you. Thank you while we're waiting for there. Now, today we're going to talk a little bit about semiconductors, something that you learned about in second and third quarter. I'm sure it's going to seem like years ago when we start doing this, but yeah, it's just been a while, and I'm sure that we can review some of this material. And you've noticed a lot of the material is reviewed that we've covered in this class, and a lot of material, well, not a lot, but some of the things here and there are concepts that we give you so that you'll be able to answer some particular questions that you might run into on an employer examination, little employer test, or on the CET. So, you know, the things that you have in your curriculum are not exactly the things that everybody thinks you should know, and so we try to give you a little bit more information than what you need, and we cover some of those high points. Okay, so let's move on. Let's get that first activity out, and here it is. Let's start with the very, very basic concepts of p-n junctions. And what you learned in second quarter when you first started working with p-n junctions was there's something called a diode. A diode is sometimes called a rectifier. It's made out of p and n materials put together. And when you put these p and n materials together, you get something in between the p and the n materials. It's called a depletion region. The depletion region looks like an insulator. And how many volts do I need to apply to the anode to make the depletion region go away to cause the diode to begin to conduct? Well, as it turns out, there's two kinds, but I want you to focus in on the silicon. I haven't seen anything in the germanium for about 5 or 6 years on the CET exam, so they're moving more towards the silicon only. But how many volts do I have to apply to an anode to make the diode begin to conduct? Well, here, how many volts? What is the voltage drop across the typical forward bias diode? Forget about the germanium. We don't have to worry about that. Well, I need how many volts? Around 0.5, 6, or 7, or even 8. But the normally the second approximation says we always use around 0.7. But hopefully you've learned when you were working with diodes, it's anywhere around 0.5, 0.6, 0.7, or 0.8. So what is the typical voltage drop that we will use for any kind of estimates? Well, it's going to be 0.7 volts. That's only if it's forward biased. Of course, what does it mean when it's reverse bias? Reverse bias is whenever you have a positive or higher voltage on the cathode. Forward bias is a higher voltage on the anode. Do you know which one's the anode? Do you know which one's the anode and which one's the cathode? Because you're going to have to know that. How about this? If I draw a diode, let's see here. Right here is the letter K, right? That's the letter K. See letter K there? And this is the cathode. So K for cathode. And over here, if you look closely, here's a letter A. And that A would be what? That would be the anode. How about that for a mnemonic to remember the cathode and the anode? Okay, what is the basic purpose of a rectifier or diode? Well, rectifier or diode means the same thing. The words are used interchangeably, so be careful of that. I'll give you a little story here. Rectifiers used to be for power supplies, and diodes used to be for communication circuits. But they both do the same thing, and they're the same kind of device. So today, in modern times, diode or rectifiers basically means either device, a diode or a rectifier, a PN junction. Now, what is the basic purpose of a diode or rectifier? It's to conduct when it's forward biased with a positive voltage on the anode, a higher voltage on the anode. It's to not conduct when it's reverse biased, a higher voltage on the cathode. And that is the basic purpose of a diode or rectifier. Too often when I hold interviews with potential employees, I'll say, what is the purpose of a diode or a rectifier? Well, it's to drop 0.7 volts. Well, that's not right. It takes 0.7 to turn on, but the purpose of a basic diode or rectifier when exposed to DC is to let current flow one way but not the other. Okay, what is the purpose if you expose it to AC, therefore? Well, let me draw an AC wave. Here's an AC wave. Isn't that a beautiful sine wave? I'm getting really good with this mouse with drawing. Not. But anyhow, here's your 0 volt level. If I'm applying a positive and negative voltage to the anode, positives here and negatives here, what will happen here? Well, if I expose it to AC, the AC becomes rectified, and depending on the direction of the diode, it will either keep one polarity or the other. So the duty here of the diode when exposed to AC is to keep one of the polarities and eliminate the other. So if the diode was pointing to the right, these would stay and these would go away. That's what would come out. If it was reverse, if you turn the diode over, these would stay and these ones would go away. So when exposed to AC, rectified, they call this rectification when you're changing an AC wave to pulsating DC. You're keeping one polarity and eliminating the other. You're changing the AC into DC. That's exactly what happens. It's pulsating DC, but it's still DC. Now, you'll have questions like this down here on the test. They're going to ask you, look at these biasing voltages. Well, first of all, do you know that a biasing voltage means the voltage that we apply to a semiconductor to get it ready to go or to get it set up? So when you hear bias, it's the voltage that we're applying to a semiconductor to get it ready to do what we want it to do. Well, look at these voltages here of these different diodes. Which one of these has a higher voltage on the anode? Well, first you need to know, here's the anode here, here's the anode here, here, and here. This is the cathode. Here's a cathode, cathode here. Here, to be forward biased, the voltage on the anode has to be a higher voltage. Well, let's see. Does this one have a higher voltage on the anode? It looks like it. This is about 0.6 volts higher than that one. So this possibly could be one. Let's look at the rest. You should always look at all the answers. Well, this one has a higher voltage on the cathode, so this one is not. This is reverse bias. Okay, now look at this one right here. This is 1.2 negative. That's way below. That's below 0 right there. That's 1.8. That's not going to be good. This has a higher voltage on the cathode. Now here's a tricky one, because it looks like this is 0.9 and this is 0.2, but in reality this is not 0.9. It's negative 0.9. Negative 0.9 is less than 0. So this is actually a lower voltage on the anode compared to the cathode. So the only possible one in this example that you might see that could possibly be forward biased would be this one. Now this one here, this one is a distractor. It's made to think, oh, 0.9 and 0.2, that's going to be 0.7. That must be the answer. No. We know that diodes will conduct, some of them, even with 0.5 or 0.6 on it. So which one will be properly forward biased? The only possible one that's forward biased is A. All right. In addition to a regular old diode, there are some other diodes that you're going to have to be familiar with. Some of these you had, some of them you did not. If you didn't, listen closely. If you did, fine. It's like watching a movie twice. All right, what are some other diodes that you must be familiar with? Okay, here they are. You need to know about Zehners. You need to know about metal oxide varistors. You need to know about varactors. I'm sure you have not had anything about a capacitive diode. So you'll have to watch this closely when I talk about it. First of all, here are the schematics. Here's a Zener. Has kind of like a Z over here. This is actually backwards. It should look like a Z. Anode, cathode, that's a Zener. Here's an MOV. It looks like that. Sometimes you see it pictured like this. Here's what we call a varactor diode. A varactor diode is a capacitive diode. When I look at it, there's a capacitor in the cathode, or sometimes the capacitor is drawn over to the right. Those are the three diodes that I have seen on the most recent CET exams. Let's talk about them. Probably 1 or 2 or 3 questions on each one. So, you know, if you have 100 points on that test, and that you have 3 questions on one particular type of diode, that's 3%. 3% you can get right. Okay, now, where is a Zener typically used? A Zener is used for voltage regulation. Do you know what a regulator is? It holds the voltage steady. Over here is your typical Zener circuit. Hopefully you covered some Zener in your second quarter. You have the unregulated voltage here, and the voltage over here that you want to regulate at is the Zener voltage. There it is. This is a 5.1 Zener. So even though I'm using 12 volts as a power supply, I'm only going to apply 5.1 volts to the load, which is connected between here and here. So the Zener is always placed in parallel with the load, and it's always reverse biased. It's always reverse biased. What does a Zener do? Explain its operation. The Zener is placed in parallel with the load that you need to regulate. And the Zener voltage across its terminals will regulate or hold the voltage steady across its anode and cathode. So if I want a 5-volt pure Zener regulator, I would buy a 5-volt Zener. If I wanted to regulate this at 12 volts, I'd buy a 12-volt Zener. So the load is placed in parallel with the Zener diode. It's right here. This would be the load. Right, in parallel with the Zener diode. So a Zener diode conducts to limit its voltage across it to the Zener voltage. A little more information here that you don't need to know for the exam. Well, this and this forms a series circuit, so whatever I have voltage here, whatever voltage I have here, the remainder is there. So these 2 voltages have to add up to the 12-volt source. But anyhow, the most important concept here, explain its operation right here. A Zener will conduct reverse bias to limit its voltage on its terminals to the Zener voltage. And by the way, I don't know if you guys talked about the Zener or not, but it's named after a guy named Mr. Zener, Dr. Zener, and he actually taught at Carnegie Mellon up until recently when he passed away. So it's a small world. A lot of components are named after famous doctors or engineers. And just letting you know, the Zener is named after Dr. Zener, who taught at Carnegie Mellon. How about that? It's a small world. Okay, what is an MOV? An MOV is a metal oxide varistor. Metal oxide varistor. It is constructed, number 11, it's constructed by placing 2 Zeners opposite. Here they're facing away, here they're facing at each other. It's the same thing. It's built by placing 2 Zeners in series facing each other. So therefore, you see this schematic, or you'll see this schematic. You'll hardly ever see this one right here. But what is its purpose? The purpose of the Zener is to protect against voltage surges. It's always placed in parallel with the load, like a Zener is. So This load might need only 120 volts, and if you were to be in a lightning storm, the purpose of this MOV is to shunt any kind of high voltage spikes coming in the line that could possibly damage this load. So it's placed in parallel, so if I get a lightning strike, all that energy gets shunted through the MOV to common before it gets to the load over here. So what is an MOV? It's a metal oxide varistor. It's built by putting two Zeners face to face, usually very high voltage Zeners, not low voltages like in a power supply. What is its purpose? It protects loads against high voltage spikes, or transients is the technical word, like lightning storms. That's a good thing that it protects against. So that's what they say here. It's a power surge. Anyone feel that power surge? That's a stupid joke. Okay. Now, how is it wired into the circuit to provide protection? It's always in parallel with the load. All right, there you go. There's two extra diodes that you haven't, that's different than the common diode. So we've talked about three: the basic rectifier diode, the Zener diode, and the MOV. Okay, there was one more. What was the other one we had to talk about? Anybody remember? The varactor diode. The varactor diode. Okay, let me tell you about the varactor diode. I'm going to try to draw this, please forgive me, but how do we build the diode? We have two materials locked up against each other, the P material and the N material. And which terminal is connected to the P material? Well, that's the anode. Which material is connected to this? What's connected to this terminal? This is the cathode. I know it's supposed to be a C, but I make it a K so I can remember about the K and the A. Now, the key feature here is when I put a P material against an N material, I get something in here. It's an insulator. What is this layer called? Because you have acceptor atoms giving up electrons, donor atoms giving up electrons to acceptor atoms, and it creates an insulator in there. What is that spot called? Right there, that's called the depletion region. There it is, right there. Now, I can control the width of that depletion region. If I put a positive voltage on the anode right here, I can make that depletion region get smaller in there. And if I get up to about 0.7 volts higher than what I have here, that depletion region gets very, very small. And it eventually goes away, and it conducts. That's how a diode works. Now, think opposite of that. What if I put a positive voltage over here? A positive voltage here makes the depletion region go away. But if I put a positive voltage here, it makes the depletion region in here get bigger. It gets bigger. Now, interesting enough, engineers found out that the P material looks like a conductor, and the N material looks like a conductor, and this is an insulator in between. Let's talk about that just for a moment. So the P material looks like a conductor, the N material looks like a conductor, and we have a cathode attached to it, and then between there is the insulator. What kind of device are you familiar with that is made with two metal plates separated by the insulator? Well, doggone, it looks like a capacitor. Every diode, if it's not conducting, looks somewhat like a capacitor. Normally, we ignore that internal capacitance when we use a diode in the normal fashion, or as a Zener, or as an MOV. But a diode that acts like a capacitor, we can take advantage of that feature and put it into a tuned circuit. You recall, we talked about tuned circuits last week. You put a capacitor with an inductor, you're creating a tuned circuit. You may remember a long time ago, all of the tuning knobs on the radio or the television, you had to grab and turn them. You were changing the capacitance. Today, what you have is a digital readout, or you just press a button, and what you're doing is you're actually changing the voltage on a diode that's reverse bias, a varactor diode. So a varactor diode is a kind of diode that is used as a capacitor. It's always wired reverse biased. And by varying the voltage reverse bias, I can change the amount of insulation in there. Putting a higher voltage on the cathode makes this depletion region get bigger. And that makes the plates get further apart. That makes what? Less capacitance. If I make this voltage here a lower reverse bias voltage, I can make the plates come closer together. Now mind you, it's not mechanically moving it closer together or further apart. You're just arbitrarily making the depletion region smaller, right here, smaller, with a lower voltage on the cathode. With a higher voltage on the cathode, this depletion region gets bigger inside of there. And that makes the plates appear to be further apart. And that's what this whole discussion is about here. Here's what they're telling you. Here's the P material that's acting like a plate of a cap. Here's the N material acting like a plate. And the dielectric is actually the depletion region. A positive voltage on the N material makes this depletion region get bigger. A lower reverse voltage on the N material makes the depletion region get smaller. So I can arbitrarily change the capacitance of the diode by increasing or decreasing the voltage on this cathode. That's how it works. Another name for a varactor diode is varicap or tuning diode. It's made to replace a capacitor in a tuning circuit. It works very, very well for digital circuits. So today in your car, unless you got a really old radio, when you turn the tuning dial, you're just changing the voltage on that capacitor. Here's how it typically would be wired. Let me draw you a little diagram here, see if it makes any sense to you. I hate to spend too much time on it because only a couple of questions. So here's my varactor diode, pad drawing, and over here is the output capacitance. Over here, right here, you have C, the capacitance of the diode, C, and over here, my tuning control is actually a DC power supply. And when I turn the knob of the tuning control, I'm actually changing the voltage of this that's applied to this diode. So when I change this voltage to a higher voltage, I have more capacitance here. A lower voltage here, I have less capacitance. That's a good, the reason why they come up with this is, in the old days, you had mechanical plates that moved further apart or closer together. But that was a problem, because mechanical things wear out. A diode, on the other hand, will not wear out unless you abuse it with too much voltage. Okay, so what happens to the capacitance as the reverse bias voltage is increased? If I put a higher voltage right here, look at this. That plate, a higher voltage, it's not right. This is not right. This is not right. I don't know where this comes from, but let me fix it. Hold on. How about that? Caught me on something here. Nope. This is the 5 picofarad, lower voltage. Okay. A higher voltage makes it further apart. This would be the 20 picofarad. They got these mixed up. How about that? So, let me just tell you again. A higher voltage on the cathode. Oh, wait. Oh, man. I am so messed up here. I am so sorry. I am so sorry. Hold on. Okay. It is correct. Gee, Willikers. Okay. Why? Let's look at this. You probably caught me in this. It took me a while to think about it. Caught me off guard. Here, the plates are further apart. The plates are further apart. I'm going to have less capacitance because I have a higher voltage because I have a bigger depletion region. It is correct. Here, when I reduce the voltage on the cathode, the depletion region is smaller, and it looks like the plates are closer together, so this would be more capacitance. So this is correct. This is correct. Okay. So what happens to the capacitance as the reverse bias voltage is increased? As the reverse bias voltage is increased, right up here, I make the depletion region larger. That makes it look like the plates are moved further apart, and I have less capacitance. If the varactor was in a tuned circuit with an inductor, say that we have a circuit here, it's a tuned circuit, an inductor, and it's in there with a varactor diode. Here's the diode, this is a capacitor on the cathode, and I'm putting on that, it's a very simplistic drawing, I'm putting power on that diode, reverse bias, and I'm changing this. Okay, so right here, if a varactor was in a tuned circuit, there it is, it's an LC tuned circuit. And what is it? It's 1 over 2 pi square root LC. 1 over 2 pi square root LC. Okay, that equals the frequency that's tuned to, the tuned frequency. Notice the L and the C are in the denominator, right? Down here. And if this goes up, the overall value goes down. This is inverse. If these go down, the overall value goes up. So let's look at this. This is a good question because about 25 or 30% of the questions that you'll run into for employer tests, screening tests or for the CET, will be questions that you have to put a couple of ideas together. So in this one, first they're checking to see if you know the relationship of L and C to the tuned frequency, and then they're checking in here to see if you know what happens to the depletion region of the capacitance if I do something with the voltage. So here they're saying if the reverse bias on the voltage on the diode was increased, if I increase the reverse bias voltage, that makes the depletion region get bigger and the capacitance to get smaller. If the capacitance gets smaller, what's going to happen to my frequency? Well, if this goes down, this has to go up. So a higher reverse bias will make a higher frequency. What about decreasing the reverse bias voltage? Well, decreasing the reverse bias voltage makes the capacitance go up because the depletion region gets smaller. And when I do that, if I increase the capacitance, that's going to make my frequency go down. So that's the relationship there. And that's how you put it in a tuned circuit. That's what you need to know. So those are the 3 kinds of diodes you need to know about. You need to know about a Zener, being a regulator, conducting reverse bias to hold the voltage steady across the anode and cathode at the Zener voltage. MOVs, sometimes called surge suppressors, they're designed to protect against overvoltage conditions. They're always placed in parallel with the load. Capacitive diodes, or varactors, or varicaps that are used reverse bias. If I increase the reverse bias, the capacitance goes down, it makes the tuning frequency go up. Those are the things you need to know about. Okay. All right. Up next, transistors, your most favorite topic. Everybody understands transistors, right? What is the basic purpose of a transistor? Any of you know? Does anybody know the basic purpose of any 3-terminal device, especially a transistor? Well, I'm going to tell you. It's not to amplify or switch. I get that answer so common. Here's how it works. I'm going to tell you. First of all, there's 3 terminals. 2 terminals that carry all of the current, and 1 terminal that is used as a controlling terminal. And so, the collector and the emitter there's always two terminals where most of the big current flows. And I use a tiny, tiny current here on the base to control this over here. That's how a transistor works. I hope you got that. By doing that, I can use it for switching or I can use it for amplification, but that is the basic purpose of a transistor, to control a ton of current in the collector and the emitter and use a tiny, tiny signal on the base to control a ton and ton of current. For example, over here in the collector and the emitter, I might be controlling 10 amps. And I can control that with a base with 1 milliamp. That would be a very, very good example. Tiny current controlling a lot of current. Tiny current, a lot of current. All right. So let's go back and talk about what you need to know about the transistor. All right. Draw and label a transistor and describe the bind method which you can remember the kind of transistor. Believe it or not, there are questions on the CET just to see if you know if it's a BJT transistor and whether it's NPN or PNP. You better not miss them ones. Those are the easy ones. And I want to tell you, if you get the easy ones right, you will get a 75. Do not blow through too quickly the easy questions. Read all the answers. Don't be fooled by distractors. If you get the easy ones right, you will almost always pass. The guys that blow through it too quickly miss the easy ones because they don't answer, they don't read all the question answers. Because remember, there might be more than 2 questions that are right. You have to pick the best possible question. But anyhow, get off topic there. What's a good way to remember if it's a PNP or NPN? I'm sure you heard this in class. Well, here's how you remember it. Look at this. This represents the diode between the base and the emitter. There's a diode in there. Turning that diode on makes the current flow. Turning that diode off shuts the current off in there. So, look, this diode is pointing outwards. A good way to remember it is not pointing in. That's a good way to remember. It's not pointing in. It's NPN. Now look at this one. This one's pointing in. Okay, it's pointing into the transistor. This is points in proudly. Points in proudly. That's how you remember. NPN and PNP, not pointing in, points in proudly. That's how you remember. Now, because right here, between the base and the emitter, and if you ever look at the construction of a transistor, how is it built? Well, let's just look at a PN and NPN. You got the collector up here, you got the emitter down here, and you got the base in the middle. And it's actually 2 diodes constructed back to back. Here's your base. And why is it called an NPN? Well, here's N material, here's P material, and here's N material. You have 2 diodes in there. Think about it. Here's the base, here's a diode pointing this way. Okay, that's the collector up there. And here's a diode pointing down here. The P material's in the middle. Remember, the P material is the anode. That's the base in this case. The emitter is down here. And the collector is up there. Emitter, collector, and here's the base. Now, the way that we turn this transistor on is we apply a voltage on the base. And to turn a transistor on, you got to forward bias this diode. And how do I forward bias this diode between here and here? I apply 0.7 on that diode's anode. That makes that diode turn on here and pulls this current right with it. So adding 0.7 onto the base is what turns the collector and the emitter on. So if you ignore the base and just think about the collector and the emitter, with 0 volts on the base, you have an open switch between the collector and the emitter. With 0.7 volts on the base, you have a closed switch between the collector and the emitter. That's how it works. I don't know if you knew that, but there you have it. 3 weeks of theory into one little lesson. So what's the typical voltage drop across the base and the emitter when the transistor is conducting? Yeah, it's 0.7. 0.7 volts, 0.7. Okay, what is there? Now, if we put You probably didn't have this in second quarter, but we got to talk about it now. You're going to have a couple of questions about this. Sometimes you can put a zener onto the base of a transistor. Look, this is a little bit tricky because the tendency is this looks like a 13-volt zener. It makes me think there's going to be 13 volts on the output of that circuit. Same here. This looks like it's a 9.2 volt zener, and if you're not careful, you think you're going to get 9.2 volts out. I'm going to tell you about that, but first let me tell you what this circuit is. This is a special regulator that utilizes a transistor along with the zener. You can use a zener just in parallel with the load and get the zener voltage. But the trouble with the zener by itself, it's very sensitive to large current loads because you can destroy the zener if the load is removed. And so quite often, to strengthen or to give a zener more power capability, they'll put it on the base of a transistor. Look, here's an NPN transistor, here's an NPN transistor. So what's happening is the input's on the base, it's the voltage that the zener is controlling, and the output is off of the emitter. So that would be a common collector, by the way, in case you didn't know that. You can ignore this right here. An emitter follower is another name for a common collector. So technically this circuit is called a common collector emitter follower pass transistor regulator. But in reality, if you just remember as this, a pass transistor regulator, you'll be doing okay. Why is it called a pass transistor regulator? Well, here's why. Over here is your load that's getting the regulated voltage. That's your load. And over here is your power coming in, your unregulated power supply. That's a battery in case you didn't notice. So I'm putting 25 volts in over here. 25 volts in. And I'm going to regulate to some output over here. Why is it called a pass transistor? Well, all the current from the power supply passes through the collector and the emitter of the transistor. That's why it's called a pass transistor. All the current passes through the transistor. It's not really using the zener to deflect any current like in a basic zener regulator. Okay, so that's what it's called. That's why it's called that. Now here's the key to solving this problem. It's very, very easy. How many volts drop between the base and the emitter? We covered that already. What is the voltage drop between the base and the emitter when a transistor is conducting? From here to here, what's in there? What does that little arrow represent that's on there? Doesn't that arrow represent a diode between the base and the emitter? So how many volts am I going to drop between the base and the emitter? Well, in there I'm going to drop 0.7 volts. So my output over here is going to be 0.7 volts less than the voltage on the base. What is the voltage on the base? Because remember, the basic purpose of a zener is to limit its reverse bias voltage to the voltage of the zener. It's going to conduct to allow what voltage right here? Not 25. What voltage is going to appear right here? This 13. I'm going to have 13 volts right there. Right here, 13. Now, how many volts do I lose right here between the base and the emitter? 0.7. So how would I find the voltage up here? 13 on the base minus 0.7. So how many volts would I have on this load right here? Yeah, 12.3. The answer to this problem would be 12.3. So that's how that works. Here's how it works one more time. First of all, it's not going to be 13 volts out. Although zeners do conduct to limit their voltage to the zener voltage across the terminals, I set the voltage right here to be 13 volts for the zener, and then I'm going to lose 0.7 volts here. So 13, the zener voltage minus 0.7 base emitter, gives me 12.3 right there. Okay, look at this one, the one on the right. It's another tricky one. I got 13, 14 volts coming in. What am I going to get out here? How would I solve this? First, find the voltage on the base. It's given, 9.2. Subtract 0.7. What is 9.2 minus 0.7? 9.2. minus 0.7, you would estimate the voltage on that terminal to be about 8.5 right here. At point A, it would be about 8.5. Don't add it. You got to always subtract it. You're losing it because the diode's in series with the Zener here. Okay. So there you have it. I can guarantee you, distractors, you're going to have this voltage, you're going to have this plus 0.7, this minus 0.7. You're going to have to pick the right voltage for the answer in the multiple choice. Oh no, not amplifiers. Oh, these are so hard. I never understood it. Oh, it's really easy. Come on. You're a second-year student. You know this stuff. Let's revisit it. You'll see how easy it is. Now, when you use a transistor for either switching or as amplifiers, they have certain types of configurations. The configuration is either common emitter or common collector. There is a common base, but you won't be tested on that. That's an RF circuit, a radio frequency. Now look at this circuit. How can I tell that this is common emitter? My signal input comes into the base. My signal output is coming off of the collector. V in is on the base, V out is on the collector. The terminal that is not being used for input or output is said to be at common. In this circuit, it's very easy to see the emitter is at common. That's why it's called common emitter. But you have to be careful of that because sometimes you will have a resistor in there. It'll look like it's not attached to common. The key feature is to look for where's the input and where's the output. A common emitter always has the input on the base and the output off of the collector. Always. That makes it a common emitter. Now, what is the typical voltage gain for a common emitter? We all know this, right? What are common emitter circuits used for? They're typically used for amplification. And so, we have a certain voltage gain from the base to the collector. I might put into this circuit here 1 millivolt peak to peak. And if I have a good power supply right here, a good power supply, I might have, say we'll make it 100 volts, just make it a really good one. I might get out of this 20 volts peak to peak. And we know that V out divided by V in gives me my voltage gain, AV. The voltage gain. The amplification factor, A, of the voltage, V. That's V out over V in. You don't have to do a calculation. I'm just telling you how you find it. My point here is common emitter amplifiers are used for one big reason. They're used to get a large amount of voltage gain. For this amp, the voltage gain is always going to be greater than 100. Sometimes 400, sometimes 1,000. So you're multiplying the input voltage by the voltage gain to get the output voltage. So what is the typical voltage gain for this amp? It's always over 100. V out over V. And you're going to get 100 times multiplication of the input to the output. So that is a simplified diagram of a common emitter. There it is. How do you know it's a common emitter? The input's on the base, the output's off the collector. What is the typical voltage gain? It's very, very high. A very, very high voltage gain. That's what you want to know. All right, how about another amplifier that you've talked about or switch? A common collector. Okay, now in addition to the power supply, where is the input being fed into this? The input is on the base. The output is off of the emitter. Anytime you have the input on the base and the output off of the emitter, it's got to be a common collector. So a common collector has the input on the base. They will always have the input on the base. and the output signal always comes off of the emitter. How's that compare to a common emitter? Common emitter, the input's on the base, the output's off the collector. Now, let's just back up here for one moment. Notice that in a common emitter, there's a resistor between the collector and the power supply. That's what allows us to use the output off the collector, because you probably learned the power supply is an AC ground, even though it's providing DC. So you have to have a resistor in it. In a common collector, you're not getting the output off of the collector. The collector is tied to AC common, which is VCC. That's why it's called a common collector. A dead giveaway for a common collector is there's no resistor in the collector. That's a dead giveaway. It has to be common collector. That's how you know it's common collector. The input's on the base, the output's off the emitter, and there's no resistor on the collector. What is another name for a common collector? Well, I'm going to show you what another name is. The input might be 1 volt peak to peak. Interesting enough, the output of a common collector is going to be the same voltage, 1 volt peak to peak. It's not designed to amplify voltage, it's designed to amplify current. And since the input is the same as the output, and the output follows the input step for step, it's sometimes called an emitter follower, because the emitter right here is following the voltage on the base, 1 for 1. You get the same voltage in and out. Sometimes a little bit less you get out. So this is called unity. When I get a voltage out that's equal to the voltage in, it's called unity. So how do you know it's common collector? The input's on the base, the output's off the emitter. And what is another name for a common collector? Another name is the emitter follower. Emitter follower. Because the output voltage on the emitter follows the input voltage on the base. What is a typical voltage gain for a common collector? We'll look over here. If V out is 1 and V in is 1, V out over V in gives you 1. It's said to be unity or 1 or less. The typical voltage gain for a common collector is 1 or less. The reason why that's important to know is if I'm scoping that and I'm looking in the inputs and the outputs, back here with a common emitter, I can see a larger voltage on channel 2 compared to a smaller voltage on channel 1 for input and output. And it's easy to see if it's working or not. But here, if I look at 1 volt on the output and 1 volt on the input, I don't see any voltage gain. It makes me think it's not working. And the neophyte or the rookie would start ripping that thing apart, thinking it's not working. But if they knew it was a common collector design, they would know that that's proper. Okay. A takeoff of the transistor, an improvement over the transistor, and that's why this guy's mad down here. This guy's mad because why you know more like MOSFET, Mr. BJT. Well, the reason behind this joke, if you didn't catch it, is FETs or MOSFETs are an improvement over the BJT. And it was because of the FET and the MOSFET that we were able to make large-scale integration or very, very tiny circuits that led to the development of the computer and the smartphone and electronics like that. And here's why. Let me tell you why. In a base, you have some current that has to flow to make that diode turn forward biased. But in a MOSFET or an FET, you don't need any current in there. It just uses a voltage on the gate to control the drain and the source turning on. Now, this is a 3-terminal device, just like a basic transistor, and it works basically the same. You have, in an FET, you have 2 terminals here that carry all of the current, the drain and the source. And by the way, I don't know if you got this before. I kind of skipped over it. Why is this called the emitter right here? It's because this emits electrons into there. And why is this called the collector? Because it collects electrons off of the emitter. And if you look at an FET here, Why is this called the drain, and why is this called the source? Well, this is the source because it's the source of the electrons going into the device, and this is called the drain because the electrons go into the drain to get out of the device. That's why it's called the drain and the source. We could call that the collector and the emitter, but they had to call it something else because it's a different kind of device. It works a little bit differently. So anyhow, the basic idea behind it, I'm sorry, I didn't mean to regress there, but the basic idea is there's a lot of current in here in the drain and the source. And by putting a higher voltage on the gate, I can shut that current off. Higher voltages on the gate shut this off in here. Lower voltages on the gate turn it on. And you can see that's why it's a little bit different than the BJT. Because a higher voltage on the base turned it on and a lower voltage shut off. That's the big difference between the two. Now, by using that kind of polarity, we don't need any current flowing in there between the gate and the source. And if you don't have any current flowing in there, it reduces the amount of heat. And that's why FETs are better. They don't have any current flowing into the gate like a BJT does, a basic transistor. So there's a diagram of a basic JFET and a basic JFET and a basic MOSFET. There you go. Same idea, same operation. Don't be confused. Major current, drain and source, controlling terminal gate. Okay. How is the operation of an FET or MOSFET similar to a transistor? Well, I'm using a tiny voltage on the gate to control a large amount of current in the drain and source here. Same thing with the transistor. Basic transistor is a lot of current in the collector and the emitter, and I'm using a tiny, tiny signal on the base to control it. So that's how it's similar. All three terminal devices are like that. I don't know if you caught that in second and third quarter or not, but they're all the same thing. Now, what makes it better? Well, one thing is a MOSFET does not amplify changes in current on its controlling terminal. It amplifies changes in voltage. It don't need current. It amplifies changes in voltage. Another thing that makes a MOSFET and an FET better is, since no current flows into this gate, it has an extremely high input impedance. The Zn is extremely high. Why is that important? It doesn't draw current from the previous circuit. It doesn't draw current from the previous circuit. That's why it's better. So what makes an FET better? What makes it better? Right here. It's better because it doesn't need current. It doesn't amplify changes in voltages. It doesn't amplify changes in current. It amplifies changes in voltage on the gate. And another reason it makes it better is it's not a current-hungry device for its base. It doesn't need any current on the gate to make it work. So it has an extremely high Zn. Think about an open and closed switch. A closed switch draws a lot of current, has a very low number of ohms. An open switch draws no current, has an extremely high number of ohms. That's why we mean by the Zn. The Zn is really high. A high number of ohms, a high Zn. Looks like an open switch between the gate and the drain. Okay, now what do we call it when we put many FETs or bipolar or regular transistors onto one component? Well, it's called an integrated circuit, an IC. When you put many, many transistors or FETs onto a very, very small package inside, it's called an integrated circuit. What is the benefit of this? Well, it makes things very, very small, and the circuits are pre-built inside. Inside of these plastic housings are circuits. And there's probably 1,000 transistors in there. And in reality, I don't know if you knew this or not, but when they build an integrated circuit, the circuit itself is right in there. It's very tiny. And we have little leads that run over here to these pins. If you look at that one below where I'm drawing, you see that right in there, you can see the actual wires. This is an actual integrated circuit. You can see the wires connecting the circuit to the pins. Let's talk about this right here for a moment. What is the typical failure mode for an IC? Usually when an IC fails, it's been abused. So here's what happens. You see these little wires here? These little wires? They will burn open. So when this wire burns open in there because there's too much current, it creates an open. So one failure mode is an open. Integrated circuits typically will exhibit an open circuit condition. Why? Because there's too much current flowing in these tiny cat hair whiskers down here that will make it burn open. Now there's another situation with an integrated circuit. Look how close those wires are in there. See how close some of them are? They're almost like a 32nd of an inch apart from each other because this is a really, really small chip. Now let me show you something here. If I have an integrated circuit, I'm only going to pick on 2 wires. I have a wire here coming out from that circuit inside. I'm talking about inside here. I'm talking about inside there, inside the chip. And I have another wire over here. Sometimes when that wire burns open, it's so catastrophic, the wire will burn open and flip and lay on top of another wire inside. So even though this wire burned open right here, it moved and flipped over on top of another wire. What does that cause? Well, inside of there, when that fails, it causes a short. So what are the 2 modes of failure for almost every integrated circuit? Generally, the tiny circuit chip inside is very, very durable. Tiny circuit chip is inside, very durable. Usually the failure mode revolves around these wires in here. They can either burn open or they can burn open and then short by laying on top of each other. Okay, now look at this. How do we number these pins? Do you remember how we number these? Look at these. How do we number? Looking down from the top, you're going to either see a little notch here or a notch here, a circle or a notch. And it makes me mad sometimes whenever you don't see that mark on there because then it's really hard to figure out what pin you're dealing with. But anyhow, you start here, then you work your way down, and then back up the other side. That's how you properly number them. You're going to see a question to ask you what is the proper numbering. And they're going to show you 4 different chips, and they're going to be numbered. You're going to have to identify that. That should be one of the easy ones for you. All right, last activity. Thyristors. Some of you had this, some of you did not. Everybody had it in 3rd quarter, but some of you did not pay attention. Or maybe you missed that day because when you're in the night classes, you miss one day. That's missing a whole week. Yeah, well, maybe you missed this one, maybe you didn't. Let's talk about it. Here's what thyristors look like right there. This one here probably can handle 1,000 amps. This one here maybe a couple of hundred of amps. This one here maybe about 300 amps. These things are very, very high power devices. Hopefully when you talked about thyristors and you worked with the small pieces in your kit, your teacher taught you that these are very, very high power devices. They're very, very important for control of power. What is the name of the special transistors used for extreme power control? Well, I just used it. They're called thyristors. Weird name, huh? You want to know where that comes from? The vacuum tubes that were used to control power before they come up with semiconductors, they were called thyratrons. So thigh, in the old days, this is not some kind of exercise machine for exercising your thighs. This is actually a semiconductor that is used to control power. Now, what are the 2 most common thyristors you will run into? There's 2 basic kinds. There is the silicon-controlled rectifier and the diagram for an SCR is basically a diode, and it has an anode and a cathode. and all you're doing is controlling the current in the anode and the cathode. Very similar to a transistor or an FET. Why? Why is it similar? You got three terminals, 1, 2, and a controlling terminal. This is where all the current flows in the anode and the cathode. Of course, it has to be forward biased to work. This terminal over here, the gate, is what controls the current in the anode and cathode. Isn't that what third quarter was all about? Hopefully you got that. You have mostly three-terminal devices, and you're controlling a ton of current in two terminals with a tiny current in the other terminal. Okay. Now, here's the basic operation. Oh, the other thyristor is a triac. It's actually two SCRs back to back. So the other type of thyristor is a triac. Let me tell you where these names come from. SCR, a rectifier right here, and it's controlled right here. A silicon rectifier and it's controlled. That's what it means. I don't know if you caught that, but there you got it. A rectifier that's made out of silicon, 0.7 volt drop, but you can control it. A silicon controlled rectifier. A triac. A triac is made to conduct AC. Look closely, and the name of the triac is, it has the letters AC in there. That's what you're going to control. And it has three terminals, tri. So tri AC, three-terminal device controlling AC. That's what it is. That's where the names come from. I did try to give you some background. It helps you to remember. Okay, the basic operation between the two. Well, when you look at this device here, it's got a rectifier in it. It can only conduct current in one direction. This one, when you look at the schematic diagram, it actually has two diodes in it, one facing up and one facing down. And then has the two terminals where all the current flows, and it has a gate on it which does the controlling. This terminal up here is called mounting terminal number 2, and this one's called mounting terminal number 1. And this is called the gate. The gate is how you control it. So this will conduct forward and reverse currents through it because you have two diodes back to back. And that's why it can conduct AC. So describe the difference in the operation between the two. An SCR can only control DC current, and a triac can control current in both directions or AC. Now, if you look at these conduction diagrams here, I'm applying AC to both of them, but the SCR will only conduct one polarity right there. That's called the conduction angle in there. But over here, look, I'm conducting here and there for the triac. So the triac can conduct both alternations. Interestingly enough, we use AC to power many SCRs, but what comes out of them for the load is actually DC. But it can still be used. Okay, next. All right, explain the operation of an SCR. It's a little bit different than a basic transistor. Let's talk about a transistor or an FET first. Let me draw a diagram here of one. Okay, what is this thing? Yeah, it's a transistor. Where's the major current flowing? Collector and emitter. So I have a lot of current flowing in there, the collector and the emitter. Now, if I have 0 volts on the base, between the collector and the emitter, it looks like an open switch. 0 volts on the base. If I put 0.7 volts on the base, current flows and it looks like a closed switch between the collector and the emitter. That's how it works. Now, if I apply 0.7 volts, it turns it on. If I remove 0.7 volts, it turns it off. So a transistor can be shut off with the base. So again, a basic transistor or an FET. I apply a certain voltage to the controlling terminal to turn it on, and I can remove the voltage and shut it off. I can do that. I can control it. What is the big difference between that and the SCR? Well, an SCR is made to handle a ton of voltage and current. And so, let me draw the SCR. Okay, let me draw the SCR. Here's the SCR. Oh, beautiful drawing there. Excuse me. So, here's where all my current is flowing, in the anode and the cathode. That's where all the current flows. When I start off, if the device is off, if the SCR is off, and there's no voltage on the gate between the anode and the cathode, it's open. But remember, that's where all the current's going to flow, is in the anode and the cathode, in there. Now, I can turn that anode and cathode on by applying 0.7 volts to the gate. When I do that, the SCR turns off. It turns on, and all the current flows. Now, here's the big difference that you have to watch for on the test. Once an SCR turns on with a voltage on the gate loses control, and you cannot shut it off with the gate. Notice over here, with this transistor, I can shut it off by changing the voltage. On a SCR, though, it will not shut off even if I remove this voltage. Even if the gate voltage goes to 0 volts, it will not shut off. It stays on. How do I shut the SCR off? I have to reset it. I have to remove the current either from the anode or from the cathode or both to shut it off. And in the schematic here of the operation of this motor, you can see it happening. Look. When I turn this on, I'm applying a voltage to the SCR, and this turns on inside of there. It turns on. A current is flowing through there. The switch is closed. And I can open this push button here, and now I have 0 volts on that gate, but this thing keeps running. The motor keeps running. If that was a basic transistor, when I lifted up that button right here, when I lift that button up, it would shut off. It would go into the off state. But an SCR loses control. The gate loses control once it's on. Now, the only way I can shut that SCR off is with this switch to interrupt the current in the anode or the cathode. When I press that button, and this button is open down here on the bottom, right here, as long as that button stays open, when I press that button and it opens the switch right here, that resets the SCR and it goes back into its off state. Then it shuts off. And it won't turn back on again until that switch on the gate is turned on. So, the operation of an SCR. I can turn an SCR on with a voltage on the gate, but once I turn it on, the gate loses control. And the only way I can shut it off is if I interrupt the current on the anode or the cathode. That's called the holding current, by the way. I have to drop below the holding current. You don't need to know that, but that's how you shut it off. So, here's a question for you. Once I turn an SCR on with a voltage on the gate, it will turn on. What happens when I remove the voltage from the gate? Well, nothing. It just stays on. That's the answer for the question, because I have to remove the current from the anode or the cathode to shut it off. That's a tricky question, because in a basic transistor, I can turn on the voltage. I can turn on the transistor with the voltage on the base or on an FET gate, but when I remove that controlling voltage, the FET in the transistor will shut off. How does that differ from an SCR? An SCR will not shut off until I remove all of the current from the anode or the cathode. All right, how is a triac physically constructed? Well, you'll remember over here you can see an SCR looks like this. Okay, just one of these. If I put two SCRs back to back and tie the gate together, I get a triac. That's how it's physically built. And that's why I can conduct in both directions. Look closely. Let's see, where's the schematic diagram? There's an SCR right there. Then when you look at this over here, you can see one. There it is. But if I flip them over and tie them together in parallel, back to back, and then tie the gates together, I have essentially a triac. That's what it is. As a matter of fact, just for your information, it's very, very popular for really high power applications to use two SCRs back to back acting as a triac. So when you see that in a control cabinet, the reason why they do that is it can handle a lot more power in two packages than a single package. When you put two SCRs together in one package like that, one package has to handle all of the heat. But if I keep them separate, it can handle a lot more heat and handle a lot more power. So typically triacs will, by themselves, will not handle as much power as an SCR package, but you will see SCRs placed in parallel back to back to replace a triac. So that's how it's constructed. I like to think of it like this, you know, I mean, if you're in the cars, you know, why do you have dual exhaust? You can get rid of all the exhaust better with two pipes than with a single exhaust. Oh, is it over? Already? No way. I want to go on for about 2 more hours. May I drone with you for 2 more hours? No, of course not. I'll start to sound like Charlie Brown's teacher. Wah, 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 wah. Fortunately, it's time for the quiz. Let's go ahead and do this quiz. Are you ready to try the quiz? Sometimes I wonder if you guys watch the video. This is the part. I gave you all the answers to the quizzes throughout this presentation, and now I'm even going to give you some more answers, some right-to-the-fact answers. And if you don't watch the video, you don't know the answers to the quiz. So let's go ahead. Let's do this quiz. Oh my. What is this circuit? What's the dead giveaway here? The collector is tied to the power supply. There's no collector resistor. The input is on the base, and the output is off of the emitter. So what is at common here? What kind of common circuit configuration is this? Well, this would be common collector. So the answer for this one would be common collector. What does a voltage gain on a common collector? A voltage gain of 1 or less. Okay. Don't even worry about common base. Don't answer common base on any problem. It's going to be common collector or common emitter. So right off the bat, you can knock off one of the bad answers. Oh, where do we see this before? All right, I'm putting 13.8 volts in. This is a pass transistor regulator with a Zener diode on its base. And I'm going to get out a certain voltage on the load. And look, they're giving me some information here. What is the voltage on this Zener right here? What is the voltage on the Zener? Well, I'm looking up here and I see the voltage on the Zener is 9.2. So the voltage of the Zener is 9.2 volts. Now look at these answers. They got a lot of distractors here. Is my answer going to be 13.8 because I'm putting 13.8 in? Is it going to be 9.2 because I'm getting 9.2 on the Zener? Because one of the tricky questions on the exam is what is the purpose of a Zener? The purpose of a Zener is to conduct so that the voltage across the Zener equals the Zener voltage. One of the other distractor questions on there is it regulates all circuits at the Zener voltage. That's not true. It conducts to limit its voltage to the Zener voltage, not that it regulates at that voltage. But anyhow, that's another question. You'll see that later. Looking over here, I got 9.2. Remember how to solve this? What's the voltage drop of this base to emitter junction? 0.7. So what happens here? I have 0.7 volts right here between the base and the emitter. Now, we got rid of this answer. That's not right. We got rid of this answer. It's not right. There's only 2 answers left. Okay? Do I subtract or do I add that voltage? Well, we know from this point right here to this point, the diode will drop 0.7 volts. We talked about that. So I'm going to lose 0.7. What is the only possible answer here, therefore? Right there, how about that? How about in these tests that you're taking, these practice quizzes and quizzes? There's answers there. When you figure it wrong, the wrong answer is always there. They're purposely there. Those wrong answers are purposely there. You need to know, play the game of knocking off the answers that you know aren't right and select from the ones that you do right. Use the process of elimination to help you narrow it down in case you don't know. Okay, look at this one. Did I see this before? Which one of these are forward biased? Which one is most likely conducting? Do you know the answer to this one? Well, here's a good distractor. Look, 0.9 and 2, 0.2. Oh, that must be it, 0.7, right? No. In reality, 0.2 minus 0.9 actually has, let's see, 1.3 volts reverse bias if I subtract those two. No, it's actually, yeah, it's a total of 1. So which one of these has the higher positive voltage on the anode? Well, this one does, but it's only 0.6, so it can't be the right answer, or could it? Yeah, it could be the right answer because we know 0.7 is an approximation. And diodes may conduct 0.5, 0.6, 0.7, 0.8, 0.9, even 1 volt may be across them, as long as the anode is the higher voltage. Okay, so that's the answer for that one. Okay, look at the schematic. What kind of transistor is that? Shucks. First, I need to know which one is the transistor. And secondly, I need to know what kind is it. Well, is it a MOSFET? No. Is it FET? No. Is there a Zener in there? No. Well, the two answers that are only good here is NPN or PNP. Let's think back. What does PNP stand for? Is it pointing in proudly, or is it not pointing in? Well, when I look at that, there it is. It's pointing in proudly. My proper answer here would be this one right here. It would be PNP. Learners, please do not miss these easy ones. Watch you don't blow by these and put the wrong answer in. Remember I said that if you get all the easy ones right, you probably will pass. How often have I seen awful drawings on the CET exam? Here's an awful drawing. Look how bad this drawing is. Yes, you as a technician have to deal with it. But anyhow, what is the question here? Which of the following ICs are numbered properly? Well, we know the little dot on the IC is where pin 1 is. So, does this one have pin 1 on the little dot? No, that's a bad one. Does this one have pin 1 on the little dot? No. So right away, I know these are not good. There's only two that I can choose from now, A and C. Let's see here. Now, what is the numbering on this? Well, we know it comes down one side and back up the other. Does this one come down one side and back up the other? No. It goes from 7 to 14. But look at this one. It comes down one side and then back up the other. That's the way it's properly labeled. So the only possible answer for this one, my friends, would be A. Okay. Again, these are really, really easy questions. You don't want to miss these. These are the ones that will knock you right out of the running. Oh my, look, here's another amplifier circuit. Huh, I wonder what this is. Well, I can see it's voltage divider bias. I can see that it's class A. There's one transistor conducting everything. But I do not have any information there telling me that it's a certain kind of common type circuit. Well, first of all, I told you, don't answer common base. None of them will be common base. Forget that one. So I have to choose And you'll rarely ever see none of the above. I'm going to tell you now, if you ever see none of the above on a CET question, you don't answer it. You never answer none of the above on a CET question. Okay, now I'm down to 2. Is this common collector or is this common emitter? How do I identify if it's common collector or common emitter? Where is the input coming into? There it is. It's coming into the base. Where's the output coming off of? It's coming off of the collector. Which terminal is not being used for the input or output? That will be the common terminal. Well, the base and the collector are used. Which one is not being used for input or output? That is the emitter. So this has to be a common emitter. And a common emitter has a large voltage gain to it. So the answer for this one would be C. Oh, not another one of these, McNeil. Well, yeah, because I don't want you to miss them. You might see 3 of them on that test. So let's get this one right this time. What is the output voltage from this? The Zener is rated at 6. The voltage drop on the base to the emitter is 0.7. And therefore, I'm going to lose 0.7 from the base to the emitter. My regulated output voltage at point A would have to be 5.3. Would I put 2 of these on your practice quiz if you weren't going to see them? No, I would not. Okay, 8, 9, and 10, rapid fire. What makes an FET better than a regular old standard transistor? What did we say were the things that made it better? Do you remember? What were they? Well, it has a high input impedance, a high Zin. And what kind of signals does it amplify? Does it amplify current or voltage? It doesn't use current to amplify. It doesn't use current on the controlling terminal. It amplifies changes in voltage. Let's see if we can find out which one of these will work. Okay. Did we say anything about it working with negative voltages? Well, it does, but so what? So does a BJT. Does it have a higher input impedance? Well, that might be a good answer, but I'm not just going to answer that yet because I want to look at the rest. Can an FET not be damaged by static? Hey, I didn't tell you this, but FETs, especially MOSFETs, can easily be damaged by static. A MOS can be damaged by static. As a matter of fact, in a MOSFET you have an insulated gate, and that insulated gate is easily damaged by static. So when you see that question, you will see it. Which of the following can be easily, which of the following needs special handling? It'll be an FET of some sort. All right, does it have a lower input impedance? No. We said it has a higher input impedance because it does not need current to make the gate work. So the only possible answer here would be this one, B. All right, look at this. Look at this blasted question right here. The main purpose of a diode. How many times have I seen students answering that? I'm going to tell you what. That answer is a bunch of happy baloney right there. Happy BS right there. All right. Does a diode conduct when reverse bias? It does not. Well, some diodes provide circuit protection, but not this one. What kind of diode provides circuit protection? And then MOV, that's a surge suppressor. All right, the only answer that you can have for that one is B. All right, what type of diode can be used as a capacitor in an LC tuning circuit? Does a Zener use as a tuning circuit? No. A PN junction, that's a regular diode. Don't be fooled by that. A rectifier, no. That has to be forward biased, these two. A light emitting diode? Nah, that could be a distractor. That could fool you into thinking, oh, when I turn the tuning knob on my radio, I see those LEDs and those displays. That must be the answer. No. The only possible answer here is varicap. Tuning diode. Variable cap or VVC or capacitive diode, they all mean the same thing. All right. That's it for today. don't forget that if you're thinking about passing the CET, I asked you to email me. Some of you evidently never check your email and you never look at the announcements on the Blackboard site. Because I get questions of material that were covered in there. And I think at the beginning of this quarter I asked you to read that twice. But big deal, it's okay. Some of us learn by our mistakes and we go back and we do things. You know, the sign of a good technician is learning from your mistakes. If you make the same mistakes over and over again, you will not be a good technician. I'm just letting you know now. So you always follow directions. You always do what the authority tells you to do. That's how you're going to be successful. By the way, if you're not taking the CET, all you need to do is pass 6 quizzes with a 6 out of 10. This is a pass-fail class. It's only worth 1 credit. And nobody will know your score except for me. All you'll see on your final grade report will be a P for passing. Nobody will know you got a 61%. It's only what I know. Nobody else knows that. It's as good as an A. A P is an A, and an NP is an F. But you don't want to take this class again, so you need to give me a little bit of attention. So, if you are thinking about taking the CET, make sure you are creating a test bank of practice and real exams, real quizzes. What you need to do for that, I mentioned this at the beginning, I'm going to review it with you now. You punch holes in all of your copies of practice and real quizzes. I give you the answers all the time. And you cross off the ones that you know. And you only study, circle the ones or yellow out the ones that you don't know, and only study those. Why study the ones that you know? It's a waste of time. Before you know it, you'll be crossing off the ones you didn't know, and you're going to know every question you're going to pass, or at least most of them. So do the new online quiz by Monday. I'll turn it on in a couple of days, and then print out the handouts for the next collaboration for week 5. I'll try to get those in there by Thursday or Friday if you want to work ahead. And it's only going to get a little more difficult. Each week is a little more difficult, so you need to keep on top of it if you're thinking about passing the CET. If you're not, whether you're taking it or not, I need to hear from you from email what your intentions are, so that if I have to correct you, I will. And if you're just floating through the class just to get a P grade for 6 out of 10, and you're just reviewing a little bit, then I'm going to let you slide through. But otherwise, I'm going to try to guide you into getting that CET. It always looks good on a resume to be a certified electronic technician. It always looks good. You got 100 resumes on your desk, and you're going through them. And I know this because I used to be an employer. I'll throw away the ones. If I see 10 of those out of the 100 that are CETs, I'll keep those and discard the rest of them. I don't care about the other stuff. You might have more experience, but that CET shows that you tried and achieved something. So, you know, I'll pick from those 10. So anyhow, I didn't mean to nag you about that, but let's go on and move on with our life and get ready for next week and make sure you take the quiz. See you next time. Thank you for being good students.